You think you know what happens when you split an atom. You've seen the images: mushroom clouds, explosions, destruction on a scale that rewrote history. You know the word fission. You know it releases energy, tremendous energy, enough to power cities or level them. The atom is split, energy comes out, and that's the story. But that's not the story, that's the aftermath. That's what happens after. What you don't know, what almost nobody explains clearly, is what actually occurs in the moment of splitting. Not the explosion, not the fireball. The split itself, the instant when one nucleus becomes two. And when you see what's really happening, when you understand the mechanism, the forces, the numbers involved, you realize something deeply disturbing, something that should make you question the stability of everything around you. Because the energy that comes out when you split an atom is not hidden somewhere inside. It's not stored in some compartment waiting to be released. It was holding the atom together. It was the glue. And when you break the nucleus apart, you're not unlocking energy. You're removing the force that was preventing something far more violent from happening all along. Let me show you what I mean. Start with the nucleus, the core of an atom. You imagine it as a tiny ball, solid, stable, sitting there doing nothing. Protons and neutrons packed together. That's what the textbook says. And it's technically true. But that picture hides the most important thing about the nucleus. It should not exist. The protons inside the nucleus are positively charged, all of them, and positive charges repel each other strongly. The electromagnetic force between two protons tries to push them apart with enormous strength. If you put two protons close together, they want to fly away from each other, violently. The closer you bring them, the stronger the repulsion, and yet, inside a nucleus, protons are crammed together at distances almost incomprehensibly small. The nucleus of a uranium atom is about 15 femtometers across. A femtometer is 10 to the minus 15 meters. That is a millionth of a billionth of a meter. At that scale, the electromagnetic repulsion between protons is monstrous. They should explode apart instantly. The nucleus should tear itself to pieces in a fraction of a nanosecond. And yet it doesn't. Uranium nuclei sit there, stable, for billions of years. Some of the uranium in the ground right now is older than the Earth itself, 4.5 billion years, and it hasn't exploded. Why not? Because there is another force, a force stronger than electromagnetism, strong enough to hold the nucleus together despite the screaming repulsion trying to rip it apart. We call it the strong nuclear force, and it is by far the most powerful force in nature. The strong force acts only at extremely short ranges, distances comparable to the size of a proton. If two protons are touching, nearly overlapping, the strong force binds them together with a strength that dwarfs the electromagnetic repulsion. It holds the nucleus together. It keeps the protons from flying apart. But the moment you separate them, even slightly, the strong force drops to nearly zero. It has no reach, no distance. It only works when particles are practically in contact. The electromagnetic repulsion, on the other hand, falls off more slowly. It has range. It reaches across the nucleus. It never turns off. So the nucleus is a balance. The strong force pulls inward, holding everything together. The electromagnetic force pushes outward, trying to tear it apart. For small nuclei, the strong force wins easily. For large nuclei, the balance becomes precarious. The electromagnetic repulsion grows stronger because there are more protons, all pushing against each other. The strong force doesn't grow as fast because it only acts locally between neighboring particles. At some point, the balance tips. Uranium-235 is right on the edge. The nucleus is barely stable. The strong force is holding it together, but just barely. It is like a boulder balanced at the top of a hill. The slightest nudge, and it rolls down. Now, here is what happens when you split it. You fire a neutron into the nucleus. The neutron has no charge, so it doesn't feel electromagnetic repulsion. It just flies in, unimpeded, and crashes into the nucleus. The nucleus absorbs it. For an instant, the nucleus has one extra neutron. It is now uranium-236, and uranium-236 is not stable, not even close. Adding that extra neutron was the nudge. The nucleus begins to vibrate, it stretches, it distorts. The protons inside are pushed slightly farther apart. And the moment they separate, even by a tiny amount, the strong force weakens. The electromagnetic repulsion does not. The protons push harder. The nucleus stretches further. The strong force weakens more. A feedback loop. Runaway. Unstable. Within a trillionth of a second, the nucleus elongates into a dumbbell shape. Two clumps of protons and neutrons connected by a thin neck. The electromagnetic repulsion in each clump is now pushing against the other clump with nothing holding them together. The neck snaps. The nucleus splits. Two fragments fly apart. Fast, extremely fast. Each fragment is a smaller nucleus, moving at about 3% of the speed of light. That is 10,000 kilometers per second. They are not drifting apart. They are exploding away from each other, driven by the electromagnetic repulsion that was being suppressed all along. And here is the disturbing part. The energy driving that explosion was always there. It was not created. It was not released from some internal reserve. It was the electromagnetic repulsion between the protons. That force was present the entire time, pushing outward with enormous strength, held in check only by the strong force. When the nucleus split, the strong force stopped acting. The electromagnetic repulsion, which was always there, finally won. The energy comes from the fact that the two fragments want to be far apart, and now nothing is stopping them. Let me give you numbers, because the numbers are what make this real. A single uranium-235 nucleus, when it splits, releases about 200 million electron volts of energy. That is the kinetic energy of the two fragments flying apart, plus some energy carried away by neutrons and gamma rays. 200 million electron volts does not sound like much, and for a single atom, it isn't. It is a tiny, tiny amount of energy, but here is the thing that should disturb you. That energy came from one atom, one nucleus. And there are trillions upon trillions of atoms and even a small amount of uranium. 1 gram of uranium-235 contains about 2.5 times 10 to the 21st atoms. If you split all of them, you release about 24,000 megawatt-hours of energy. That is roughly the amount of energy a large city uses in a day, from 1 gram. 1 gram of matter, if every nucleus splits, releases as much energy as burning 3,000 tons of coal. Think about that ratio, 3 million to 1. The energy density of nuclear fission is 3 million times higher than chemical combustion. Not twice as high, not 100 times, 3 million times. This is not because fission is special or magical. This is because the strong nuclear force is extraordinarily powerful, and the electromagnetic repulsion at nuclear distances is extraordinarily strong. When you break a nucleus apart, you are tapping into forces that are fundamentally stronger than anything chemistry can access. Chemical reactions involve rearranging electrons. The electromagnetic force at atomic distances. Nuclear reactions involve rearranging protons and neutrons. The strong force at nuclear distances. The energy scales are simply different, orders of magnitude different, and this should bother you, because it means that every heavy nucleus, uranium, thorium, plutonium, all of them, is sitting on a vast reserve of potential energy. Not stored energy, potential energy. The energy of charged particles held together against their mutual repulsion by the thinnest possible margin. Most of the time, they sit there, stable, doing nothing. The strong force wins. But under the right conditions, if you disturb them just slightly, they can release that energy, suddenly, violently, all at once. Now let's talk about what happens to the fragments. When the nucleus splits, it doesn't split into two equal pieces. The split is asymmetric. One fragment is usually larger than the other. Typical products might be krypton and barium, or strontium and xenon. Different isotopes, different combinations, but always two medium-sized nuclei instead of one large one. And here's the key. Those two fragments are unstable. Uranium-235 was barely stable. The fragments freshly created are not stable at all. They have too many neutrons. The ratio of neutrons to protons that works for a large nucleus does not work for a medium-sized nucleus. They are born radioactive. They immediately start decaying, emitting beta particles, gamma rays, transforming into other elements. This process releases more energy, not as much as the initial split, but still significant, and it continues for seconds, minutes, days, years. The fragments are hot, both thermally and radioactively. They do not calm down quickly. This is why nuclear waste is dangerous. It is not just that it is radioactive. It is that the waste products are the fragments from fission, and those fragments are violently unstable. They were created in an unnatural state, and they spend decades trying to get back to stability, emitting radiation the entire time. Every split nucleus leaves behind two fragments that did not exist before, elements that were not present, isotopes that are not naturally abundant, and all of them are decaying, all of them are radiating, all of them are energetically trying to reach a more stable configuration. Here is another thing nobody explains clearly enough. When the nucleus splits, it also releases neutrons, usually 2 or 3. These neutrons were part of the original uranium nucleus. When it split, they were not bound to either fragment. They just flew off, free. And those free neutrons are the key to everything that follows, because a free neutron can hit another uranium nucleus, which splits, releasing more neutrons, which hit more nuclei, which split, releasing even more neutrons. This is a chain reaction. 1 split triggers 2, 2 trigger 4, 4 trigger 8. Exponential growth. In a critical mass of uranium, this process runs away. The number of splits doubles every generation. If each generation takes a nanosecond, you get about 80 generations in a microsecond. 2 to the 80th power is about 10 to the 24th. If you start with 1 split, after 80 generations, you have 10 to the 24th splits. That is more atoms than exist in a kilogram of uranium. In 1 microsecond, the entire mass has fissioned. All the energy released at once. That is a nuclear explosion, not because the atoms are special, not because of some exotic physics, because the process is exponential, and exponential growth, if unchecked, goes from tiny to enormous in almost no time. The critical mass for uranium-235 is about 50 kilograms, a sphere about the size of a grapefruit. If you have less than that, neutrons escape before they hit another nucleus. The chain reaction dies out. If you have more, the chain reaction sustains itself. If you have significantly more, or if you compress it, the chain reaction accelerates. The energy release becomes explosive. 50 kilograms of uranium, properly configured, is enough to destroy a city, not because each atom is powerful, but because 50 kilograms contains 10 to the 25 atoms, and if even a small fraction of them split in a microsecond, the energy release is beyond anything chemical reactions can achieve. Now think about what this means for control. A nuclear reactor is a controlled chain reaction. You want the reaction to continue, but not accelerate. You want exactly 1 neutron from each split to cause another split, not 0 or the reaction stops, not 2 or it runs away. 1. Engineers achieve this by carefully controlling the environment. They use materials that absorb neutrons, called control rods, to regulate the reaction rate. They use moderators to slow down neutrons, because slow neutrons are more likely to cause fission than fast neutrons. They design the reactor geometry so that neutrons are likely to hit fuel rather than escape. But the fundamental challenge is this: the reaction wants to grow exponentially. That is its natural tendency. You are trying to hold it at exactly the threshold where it neither grows nor dies. It is like balancing a pencil on its tip. Possible, but requiring constant adjustment. If the balance tips slightly toward growth, the power output increases. The reactor heats up. The heat changes the neutron behavior, which usually provides negative feedback, slowing the reaction. But if the feedback is not strong enough, or if the reactor is poorly designed, the power can increase faster than the control systems can respond. That is what happened at Chernobyl. A poorly designed reactor with positive feedback under certain conditions. The operators disabled safety systems and pushed the reactor into an unstable state. The reaction rate increased, the power spiked, the fuel overheated, the reactor destroyed itself. Not because of an explosion in the nuclear sense. Chernobyl was not a nuclear bomb. It was a steam explosion. The reactor got so hot that water flashed to steam. The pressure ruptured the containment and the core was exposed. But the damage was done by a runaway chain reaction that the control systems could not stop in time. The reactor was trying to go exponential. The design allowed it. The operators created the conditions. And exponential growth does not wait. Let's go back to the disturbing part. Every uranium nucleus is held together by force, the strong nuclear force. Without it, the electromagnetic repulsion would tear the nucleus apart instantly. With it, the nucleus is stable, metastable really, balanced on a knife edge. When you split the nucleus, you are not adding energy. You are removing the thing that was holding the energy in check. The strong force was doing work, constantly, every instant, preventing the nucleus from exploding. When the nucleus splits, that work stops. The electromagnetic repulsion, which was there all along, takes over. The energy release is not the creation of something new. It is the sudden absence of restraint. Think about a compressed spring. You push it down, hold it in place. The spring is storing energy, pushing back against your hand. As long as you hold it, nothing happens. The moment you let go, the spring expands violently. The energy was there the whole time. You were just preventing it from being released. The nucleus is the same. The strong force is your hand. The electromagnetic repulsion is the spring. For billions of years, the strong force holds. Then you split the nucleus. The strong force stops acting. The spring is released. The explosion is not the energy appearing, it is the energy that was always there, finally allowed to act. And this is true for every heavy nucleus. Uranium, thorium, plutonium, all of them are held together by force against repulsion, in a state that is barely stable. They look calm, they look solid, but internally they are under constant tension, enormous forces in equilibrium. And if that equilibrium breaks, the energy comes out, suddenly, completely. Here is something else that should disturb you. Fission is not rare. It happens naturally. Uranium-238, the most common isotope, undergoes spontaneous fission occasionally. Very rarely, but it happens. No external neutron required. The nucleus just vibrates a little too much, stretches a little too far, and splits, randomly. For uranium-238, the half-life for spontaneous fission is about 10 to the 16th years. That is 1,000,000 times longer than the age of the universe. So for practical purposes, it does not happen. But it does happen, occasionally. One nucleus here, one there, splitting for no reason other than quantum probability. Uranium-235 is more prone to induced fission, but it still requires a neutron to trigger it reliably. However, there are isotopes that are even less stable. Californium-252, for example, undergoes spontaneous fission with a half-life of about 85 years. A sample of californium-252 will split atoms on its own continuously without any external trigger. This means that fission is not something humans invented. It is a natural process, a consequence of the fact that large nuclei are barely stable, held together by a force that is strong but short-ranged, opposed by a force that is weaker but longer-ranged. At some size, the balance breaks. The nucleus becomes so unstable that it splits on its own. Humans did not discover a new phenomenon. We discovered how to make it happen faster, how to choose when and where, how to create the conditions for a chain reaction. But the underlying instability was always there. Every heavy nucleus is a potential source of enormous energy, waiting for the right conditions to release it. Now consider this. The energy released in fission is mass. Einstein's equation, E equals mc squared. Energy and mass are equivalent. When a nucleus splits, the total mass of the fragments is slightly less than the mass of the original nucleus. The difference, converted to energy using c squared, is the energy released. For uranium-235, the mass difference is about 0.1%. 1/10 of 1% of the original mass is converted to energy. That tiny fraction multiplied by c squared, a huge number, gives you the energy of fission. This is not metaphorical. The fragments actually weigh less than the original nucleus. The missing mass became energy, kinetic energy of the fragments, radiation, heat. It left the system as energy, and the system became lighter. Mass is not conserved in nuclear reactions. Only mass energy is conserved. And that should be deeply strange to you. Matter can turn into energy, not by annihilation with antimatter, not by some exotic process, just by rearranging the nucleus. The strong force, when it binds particles together, reduces the total mass of the system. The bound nucleus weighs less than the sum of its parts. This is called binding energy. It is the energy equivalent of the missing mass. When you split the nucleus, you are reducing the binding energy. The system has less binding, so more of the mass becomes available as kinetic energy. You are not destroying matter. You are converting binding energy into kinetic energy. But the effect is the same. The fragments weigh less. The difference is energy. And that energy, released suddenly, is what makes fission so powerful. Here's the final thing, the thing that ties it all together. The nucleus is not solid. It is not a thing. It is a configuration, a pattern, a bound state of quantum fields. The protons and neutrons inside are not sitting still. They are in constant motion, fluctuating, held together by the exchange of particles called gluons and pions. The strong force is not a static glue. It is a dynamic process, constantly active, constantly working to keep the nucleus from flying apart. When you split the nucleus, you are not breaking an object. You are disrupting a pattern. The configuration that was stable becomes unstable. The forces that were balanced become unbalanced. The particles that were bound become free, and the energy that was holding the configuration together is released as kinetic energy of the fragments. This is not destruction in the sense of annihilation. The protons and neutrons still exist. They just reconfigure into two smaller nuclei, but the process releases energy because the new configuration has less binding energy than the old one. The difference is what you feel as heat, light, radiation, and kinetic energy, and the amount of energy released is enormous because the binding energy of the nucleus is enormous. The strong force is the strongest force in nature. Breaking that binding, even partially, releases energy on a scale that nothing in chemistry can match. So here is what you are left with. When you split an atom, you are not unlocking hidden energy. You are removing the force that was holding back a far more violent process. The electromagnetic repulsion was there all along, trying to tear the nucleus apart. The strong force was holding it in check. When the nucleus splits, the strong force stops acting. The repulsion wins. The fragments explode apart. The energy was always there. The instability was always there. The potential for violence was always there. Every heavy nucleus is a barely stable configuration of particles held together by force against mutual repulsion. And under the right conditions, that balance breaks. What happens when you split an atom is not the creation of energy. It is the sudden removal of constraint. The universe was holding something back. You let it go. And what was restrained is far more powerful than most people realize. Not because atoms are magical, because the forces inside the nucleus are incomprehensibly strong, and the balance holding them in check is incomprehensibly delicate. That is what makes fission disturbing, not the explosion. The realization that the explosion was always possible, always there, waiting, held back by a force that, under the right conditions, can fail. And when it fails, the energy that comes out is not new, it is old, ancient, bound into the nucleus when the atom was formed, billions of years ago, waiting, patient, inevitable. You did not create the energy, you just stopped preventing it, and the universe does not care whether you are ready for what happens next.